Welcome to this explainer. If you've ever just sat there staring at this absolutely massive list of machine learning algorithms and felt, well, totally overwhelmed, you are definitely in the right place. Today, we're focusing squarely on what is arguably the most practical challenge in data science, learning algorithm selection. We're drawing directly from section 5.2 of Andrei Burkhoff's 100-page machine learning book to really cut through all that noise and figure out exactly how to pick the right tool for the job. Okay, let's dive into this with a quote from the statistician George Box, which is basically our North Star for today. He said all models are wrong, but some are useful. And that's exactly it. Our goal here isn't to find some kind of mathematical perfection that explains the entire universe. No, our goal is to find the most useful model for your specific problem, given your specific constraints, without wasting literally weeks of your life just guessing and checking. To find that useful model, we've broken things down into a really structured framework for this explainer. We'll cover the dilemma, business and hardware realities, the shape of the data, the need for speed, and finally, the ultimate cheat sheet. Basically, we've taken Burkhoff's 7 vital selection questions and grouped them into these clean, logical buckets. Part 1, the dilemma, picking the right tool. So why is choosing an algorithm so ridiculously hard? Well, mostly because time is strictly limited. Let me ask you, do you have unlimited time to test every single algorithm that exists against your dataset? Yeah, neither do I. In the real world, nobody does. Because of that, Burkhoff gives us these 7 specific constraint questions, and you should really think of these not as hurdles, but as this brilliant, rapid process of elimination. Every single time you answer one of these, you instantly cross a bunch of algorithms off your list, whittling it all down until you're left with your perfect match. Section 2. Business and hardware realities. Okay, before we even think about touching the underlying math or looking at the geometry of our data, we have to look at reality. And the very first reality check is about explainability. Does your model have to be explained to a non-technical audience? Like, if you're reporting to a board of directors, you probably can't use highly accurate black box models like deep neural networks or complex ensembles. Why? Because explaining exactly why they made a specific prediction is incredibly difficult. On the flip side, if you absolutely need transparency, you're instantly routed toward explainable models like k-nearest neighbors, linear regression, or decision trees. Sure, they might sacrifice a tiny bit of accuracy, but their straightforward logic is a massive business asset. Next up, we hit a very hard hardware constraint, and that's your memory. Can your entire dataset be fully loaded right into the RAM of your server or your PC? If the answer is yes, great. The menu is completely open. But if your data is just way too massive to fit into memory, your funnel immediately narrows. You're basically forced to abandon standard methods and shift entirely to incremental learning algorithms. These are specifically designed to build and improve the model by adding data gradually, just piece by piece. Section 3, the shape of the data. Now, what's really interesting about this slide is how we can think of algorithms almost like picky eaters. You have to ask yourself, how many training examples do you have, and how many features does each example have? Neural networks and gradient boosting are basically the competitive eaters of the machine learning world. They're built to gracefully inhale millions of features and massive data sets. But other algorithms, take support vector machines, for example, they have a much more modest appetite, and they'll completely choke if you overwhelm them with too much data. We also have to look at what your data is actually made of. Is it categorical? Like colors or categories, or is it purely numerical, or maybe a mix? A lot of algorithms, and this includes SVMs, logistic regression, and KNN, strictly demand numerical data. If you have categorical features, you can't just plug them right in. Actually, scratch that. You have to translate those categories into numbers first. You'd use conversion techniques like one-hot encoding before the algorithm can even begin to digest them. Which leads us to a fundamental geometry question you have to ask. Is your data linearly separable? You want to think about this carefully because the shape of your data literally makes or breaks your algorithm choice. So if your data can be modeled using a straight line or a flat plane, meaning it is linearly separable, you are in luck. A simple yes here opens the door to highly efficient linear models. We're talking an SVM with a linear kernel, logistic regression, or just linear regression. But if your data is this complex, tangled mess, meaning it's nonlinear, those simple tools are going to fail for sure. A no to this question mandates that you bring in the heavy hitters, like deep neural networks or ensemble algorithms. All right, moving to section 4, the need for speed. So, the crucial point here is that there's a huge difference between the time it takes to build a model in the lab versus actually using it out in the real world. We're dealing with a strict trade-off between training speed and prediction speed. Take neural networks. They are notoriously slow to train, sometimes taking hours or even days. But once they're deployed, incredibly fast at generating predictions. Simple algorithms like regressions or decision trees, fast at both. Now, KNN is lightning fast to train because it essentially just memorizes the data, but it can be much, much slower when it's actually making predictions. Oh, and if training speed is a major bottleneck for you, Burkhoff points out that algorithms like random forests can significantly cut down that training time, assuming you have a machine with multiple CPU cores. And that brings us to Section 5, the ultimate cheat sheet. And this brilliantly illustrates everything we've been talking about. So we've filtered by explainability, RAM, data size, data shape, and speed constraints. What you're looking at is the famous scikit-learn algorithm cheat sheet referenced in the text. Look at the flow here. You start right there at the orange circle, and based on the exact constraints we just went over, things like having more than 50 samples, whether you're predicting a category or a quantity, whether you have labeled data, you just follow the arrows. It is a literal map guiding you past the algorithms that definitely won't work, straight to the ones that will. It's just such a pragmatic, step-by-step visual cheat code. Like, let's say you're predicting a category with fewer than 100K samples. It routes you directly to a linear SVC. If that's not working, it pushes you right over to K-nearest, and so on. It perfectly visualizes Burkhoff's core philosophy here. Don't test everything. Test intelligently, based on your constraints. But hey, what if you've gone through all the questions, you've followed the map perfectly, and you still have 2 or 3 solid candidates left? Well, the source text offers one final, ultimate tiebreaker. If you really don't want to guess and time permits, you simply test those remaining algorithms directly on your validation set. Let the actual performance data make that final decision for you. Which leaves us with a pretty fascinating thought to end this explainer on. If we have flowcharts and, increasingly, automated systems that can process these constraints and pick the absolute best algorithm for us, what exactly is the true role of the data scientist? Perhaps the real skill isn't memorizing the math of 50 different models anymore. Perhaps it's knowing the business context, understanding those hardware realities, and knowing how to ask the right questions of the data in the very first place. Something to think about as you gear up for your next project. Thanks so much for joining me on this explainer, and I will catch you in the next one.